Okay, today we're going to talk about 5.2, which is excuse me, sigma notation and limits of a finite sum. And this is going to get us to um, Friday, which is going to be basically using sigma notation. And we're going to take limits of we're going to take the limit as the limit of n goes to infinity of a finite sub, so we get almost an infinite sum of little rectangles, little approximating rectangles underneath the curve to get the true area of the curve. So um, hopefully this isn't the first time you've seen this, but sigma notation is um, is this is a capital Greek sigma right here. It means summation notation. So basically this is telling us to add a bunch of things up. Here we have these a sub k's. So usually you can think of this as a sequence of numbers that are going to be defined in a particular way. Down here, this is the start of the index, how we're indexing it. We're starting at k equals 1, and then this is telling us where we're going to end, and we're going to end at when k equals n. So if we're going to like expand this out and figure out what we're actually adding, we start when k equals 1, and we just plug the 1 in for the k there. So we have a sub 1 plus. Then after 1, we go to 2. So we have plus a sub 2, plus a sub 3, plus a sub 4, et cetera, et cetera, et cetera. And this continues on all the way until we get up to the number n. And this right here is really what this sigma notation represents. This is a shorthand method of writing a sum of something. So that's this. So the rules of this are much like the rules of limit. It's called a linear operator, which is to say that if we have the sum of a sub k plus or minus b sub k, well, we can take the sums of the a sub k's and either add or subtract those from the sum of b sub k's. And that's what this is saying right here. Now, if we have a constant, some number times a sub k, we can always pull that number through. So we can pull that number through and then multiply this whole sum by that number, which is almost like factoring if you think about that. Like if we were up here and this was a c here, we'd have a c here, 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 here. So we could have really just factored that c out, brought it in front. And that's a way to think about, think about that rule. If we're adding up a constant a bunch of numbers of times, this would be like adding up, let's say c is 5. So when k equals 1, c is 5. When k equals 2, c is 5. When k equals 3, c is 5. So we'd have 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5. And we'd have n copies of that 5, or the c as we have here. So if we have n copies that we're adding together of that, then that really is just multiplication. So that's why we get this n times c. Now, there's a couple formulas, and we're not having proctored assessments, especially not for this first test. So you don't need to memorize these, but you will need a small working knowledge of how to do these. Now, and I'm going to briefly talk about them. I'm not like maybe in class on Wednesday if you really want me to prove one of these, you can prove it, but it's generally something that you do in a higher level class, and you prove these using something called induction. So this right here are three formulas that we're going to be using. This is the sum of k when k equals 1 to n. So if we think about what this is like when k equals 1, this is 1, plus when k equals 2, this is like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, all the way up to n. If we add all of the integers from 1 to n together, you get n times n plus 1 over 2. And there's a really quick and easy proof for that, but I'm not going to do it now. It's not important. We're just using this fact. We can assume that it is in fact true. This is 1 when k runs from 1 to n, the sum of this when k squared. So we have like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way up to whatever n squared is. If you add up all those numbers, it's going to be n times n plus 1 times 2n plus 1 all over 6, where this is the end of the indexing. Same here, end of the indexing. If this was the sum from 1 to 100, we would just plug 100 in for our n's. If this was the sum from 1 to 53, where we're adding up 1 squared plus 2 squared plus 3 squared all the way up to 53 squared, we just plug 53 in for n. Same thing here. The only difference is k is being cubed. So we have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, so on and so forth. When we add those all up, if we're summing up the cubic numbers, between 1 and 24. This would be a 24 up here. We put a 24 in there, calculate, that's what we get. Now, next we're going to talk about a Riemann sum. And a Riemann sum is basically what we were doing yesterday, or what we were doing with approximating rectangles, approximating area using rectangles. So what we're going to do with this Riemann sum is make some assumptions. And our assumption is going to be that this function f right here is going to be continuous from a to b. Okay, so if f is continuous from a to b, the limit exists. The limit equals the function value at each value in here, and we can draw this without picking our pencil off the paper. Now let's assume we're going to break this into n subintervals or n rectangles. If we do that, if we think about that, when we talked yesterday, our little delta x, our little equal width subintervals, we always take the n point minus the starting point, our b minus a over n. That's going to be our delta x. So right here, if a, this endpoint right here, is going to be our x sub 0, our first one. If we move a little delta x over, that's going to be our x sub 1. If we move another little delta x over, that's our x sub 2. If we move another little delta x over, that'd be our x sub 3, and so on and so forth, all the way up to b, where b equals the x sub n. Because if you think about this, we're having n total rectangles. If we start at 0, that would be 1, 2, 3, keep counting, and we'd have n total rectangles there. So we call these partitions. So the partitions of this little interval from a to b would be the set of x sub 0, x sub 1, all the way up to x sub n. Now the Riemann sum, like, we're just building up some machinery. The Riemann sum is a partial sum. If you remember from like an algebra course, like a college algebra, pre-calculus, something like that. S sub n is a partial sum. We're adding up a finite number of things here. So the Riemann sum, how it's defined for the function f over the interval ab, and we're really just calculating rectangles, like the area of rectangles again. S sub n is the sum from k equals 1 to n of f of a plus k. Well, k is what we're indexing with. A is our starting point over here. B minus a over n. This is a little delta x. So another way of thinking about this is f of a plus k times delta x. This right here is just telling us our height. Now think about it for 1 second. If k equals 1, a plus a little delta x. If we have a plus a little delta x, we're starting at k equals 1. That would be putting us over here. So it's giving us a right endpoint. This is giving us a right endpoint approximation for the height. So f of this is going to be our height of the function right here, and it's going to be using the right endpoint. B minus a over n is our width. That's our little delta n. So this is the height. This is the width. We're adding, this is just shorthand. We're adding up a bunch of rectangles, just like we did in the last class, but just a little bit differently. So that's the Riemann sum. And this is going to be the big thing on Friday. We talk about the Riemann sum. Basically, what we're going to do is we're going to take the limit of s sub n as n goes to infinity. That's going to give us an infinite number of rectangles. It's going to give us the true area under the curve. And that's what we're really looking for. So that being said, we're going to do a little bit of work with sums, a little bit of work with some other things. So I'm just going to talk through the examples that we do have done. So this is write the sums without sigma notation. So here, if we have the sum of k minus 1 over k equals 1 to 3, well, we're starting when k equals 1, plug 1 in these k's. That's what you're seeing right here. 1 minus 1 over 1. Now we let k equal 2. Plug 2 in for all the k's. That's what this is. So the sum, the sigma right here is telling us to add things together. This is telling us the the bounds in which we're going to add. So k equals 1 is right here. We let k equal 2. Finally go to the end index, k equals 3. Plug it in. 1 minus 1 over 0, 0. 2 minus 1 over 2 is 1/2. 3 minus 1 is 2, so we have 2/3. We add these all together, we get 5/6. So that's We're writing this without sigma notation and then computing what the actual value is. Down here, when we have our sigma notation, we have k equals 1 to 5, and we're taking the sum of sine of k pi. So we're going to let k equal 1, 2, 3, 4, and 5. So sine of 1 times pi, sine of 2 times pi, sine of 3 times pi, sine of 4 times pi, sine of 5 times pi. And I mean, we can put these in our calculator, but we should know at this point that sine of pi's, or at least integer value pi's, is going to be 0. Those are the x-intercepts of the graph, or you can think of those as basically like on the unit circle, where the unit circle is hitting the x-axis, the y value there is 0. So we have 0 plus 0 plus 0 plus 0, 0, a lot of zeros. The next question we're going to do is this one right here, and it's saying which formula is not equivalent. Now look, this is what you're going to be getting in MyMathLab, A, B, and C. Like, don't try to think like, oh, this one doesn't look like that, so it's not the same, or this and that are not the same. Like, write out what the sum is. Here, if we have k equals 1 to 4, so the sum of k equals 1 to 4 of k minus 1 squared, plug the 1 in, plug the 2 in, plug the 3 in, plug the 4 in. You get that right here. Here we have the sum of k equals negative 1 to 3 of k plus 1 squared. Plug our negative 1 in, plug our negative 1 in. Then we go to 0, then we go to 1, then we go to 2, then we go to 3. Plugging these things in. Excuse me, we're going to get that right here. If we plug our k equals, now we're taking the sum of k equals negative 3 to 1. So here we have negative 3 squared, then we add 1 to this, negative 2 squared, then we add 1 to this, negative 1 squared, then we add 0 squared, then we have 1 squared. And we want to compare which ones of these are the same. Now here, when we go all the way from k equals negative 1 to 3, we need to add this third one in. We only did negative 1, negative 2, or excuse me, negative 1 in here, 0 in here, 1 in here, 2 in here. If we plug 3 in here, we'd have plus a 4 squared. If we look at this one and this one are equivalent. They're not the same as that one. This is the one that does not belong. So that's there's incorrect. So when trying to figure out which formula is not equivalent to the others, write all the terms out and then figure out what's going on. Now, if we're going to express a series in sigma notation, you want to think about what is the rule that ties these things together. So this is what they're going to be giving you in MyMathLab. This is what we're going to be doing right now. If we have 2 plus 4 plus 6 plus 8 plus 10, these we're adding up the even numbers. Even numbers are 2 times. They have a factor of 2 in them. That's just by the nature of what they are. That's what they have. So here, when we're doing this, we have 1, 2, 3, 4, 5 numbers we're adding together. We can think that this is 2 times 1, 2 times 2, 2 times 3, 2 times 4, and 2 times 5. So that factor of 2 is consistent, and that's why I have the 2 right there. Now, because this is 2 times 1, 2 times 2, 2 times 2, 2 times 4, and 2 times 5, if we let k equal 1 to 5, 2k, that is going to be this right here. Now, there's different ways to write this, but this is going to be the easiest one you have. When we look at this right here, if we have positive, negative, positive, negative, positive, and they alternate, it's called an alternating series, or we're going to have this alternating sum right here. And because it's alternating positive to negative, you're going to have a factor of negative 1 in here. It could be to the k. If you're getting your pluses and minuses off, you can either add 1 or subtract 1 to the k up here, and it will move your positives and negatives over 1, either to the right or the left. It doesn't matter. When you're moving things to the right or the left, and there's only 2 choices, it doesn't really matter. But here, if we think about this, and we think about 1 as 1 over 1, this is 1 over 2, this is 1 over 3, 1 over 4, and 1 over 5. If you just think about it like that really quickly, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, what's increasing is the denominators here, going from 1 to 5. So if we have k equals 1 to 5 of 1 over k, that's what that's going to be that sum. And if it was just 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, we wouldn't need this little alternating piece right there, but it's not, it alternates. So usually I would try -1 to the k, but if we plug 1 in here, -1 to the first power is -1. 1 over 1 is 1. That would give us a -1 here. We don't want that. So we have to either add or subtract 1 to that k. Doesn't really matter which you choose. Both of them are equivalent formulas, like we saw up here. Sometimes you'll have formulas that are equivalent. They don't look the same. These things do not look the same, but the sum is equivalent. So the formulas are, in fact, equivalent. Here we're going to evaluate the sum, and what we're going to do is we're evaluating the sum using the sigma notation from up here. So we're going to be looking at these formulas right here. So those formulas right here, and we're going to be evaluating those sums. So here, if we have the sum of 7 from 1 to 500 be 7 plus 7 plus 7 plus 7 plus 7 plus 7 plus 7, and we'd have 500 copies of that 7. Well, if you're adding 7 together 500 times, it's really 7 times 500, which falls into this if we're adding up a constant repetitively, this right here, adding up 7 from 1 to 500, it would just be 7 times 500. So 3,500 right there is what we're going to get. Now, if we have the sum of k equals 1 to n, we don't know where this is going to end. But if we have the sum of k minus 1 from k equaling 1 to n, we can use that linear operator, like power of the sum, to say this is going to be the sum of k from k equals 1 to n minus the sum of 1 from k equals 1 to n. Well, the sum of k from k equals 1 to n, this really should be in terms of n now, it would be n times n plus 1 over n. Oh, these are, ooh, I get smushed up. That should be an n, so that should be an n, that should be an n. Similarly, if we have the sum of k equals 1 to n here of 1, we're adding that constant together just like this. We're adding 1 together n times. That should just be an n. So I didn't change my my variable and indexing there. That's bad form. That should be an n. 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 But that's how we use the summation notation. So the last thing that we have to do, or that we're going to do, and I'm going to talk you through this, and we'll do it in class as well, is we're going to use a Riemann sum, and we're going to write these Riemann sums out. And we're going to graph the partition into 4 subintervals of equal length. We're going to find the sum of k equals 1 to 4. That's a 4 up there because we have 4 subintervals. This will be a 4 up here. So we're taking the sum from k equals 1 to 4 of f of ck, where ck is going to be the right or left endpoints. We'll figure that out here in a minute, times our little delta k, which this is, again, height times width. We're going to do this in 3 capacities. We're going to do it for the left endpoints, we're going to do it for the right endpoints, and we're going to do it for the midpoints. So we're going to figure out what's going on here. So if our function we're looking at here is f of x equals x squared minus 1, this is just a parabola that's been shifted down 1 unit, which is what this graph is supposed to represent here. If we're looking for this on the interval from 0 to 2, one thing we want to know is, what is our delta x? Well, delta x is always b minus a over n, because we have 4 little rectangles or 4 partitions. Our 2 minus 0 over 4 is going to give us 1/2. Okay. Now, if we're doing a left endpoint, we want the first actual piece here to be evaluated. We want the height to be at 0. So when we do this, we're going to have to plug this in, and we really don't want anything going on right here. So and because we want this to evaluate at 0, what we have to do is we have to move some things around. And this is going to be true for all of them. So what I want you to look at here is this. If we want this to be at 0, we know we're going to add a little delta x to the straight. What's going on? We should wake up now. Sorry about that. So when we do this, if I put a k minus 1 up here, and if we go back to the Riemann sum up here for a second, notice it's k times b minus a over n. So if we have k times b minus a over n, and this is b minus a over n, when I come down here, our b minus a over n, this really should be a 4 here. This should be a 4, and that should be a 4, but it doesn't really matter. I'm just doing these in terms of n subintervals. So our k times our 2 minus 0 would be a 2 there. This right here, the negative 1 here, is going to counteract us being a right endpoint. So when we plug 1 in here, 1 minus 1 is 0, 0 over anything 0, plus 0, 0. So we're starting at the left endpoint of this letter A right here. So this really is a left endpoint vision. Now, if we want to do a right endpoint, we don't want this minus 1 here, because we really don't want to start at 0. We want to start one piece over. Well, if we're doing this into n subintervals, we're just going to have this 1/2 right there. So we're going to have a k over, this really would be a 2, and that would be a 2. But this, now notice, when we're doing the left endpoint, we have the k minus 1 here. When we're doing the right endpoint, we just have the k right there. The only other thing that we're going to do is the midpoint. And the midpoint of this is just a little bit weird. Now, if you think about each of these little delta x's being 1/2, this starts at 0, and then it goes to 1/2. Halfway in between 0 and 1/2 would be 1/4. That's why here we started at 0 and added this. Really, we'd put 0 plus k over n in the right endpoint. Here, we're not starting at 0 because we want to start at the midpoint. Here we're starting at 0. Here we're starting at 0, but moving over one whole delta x. Here we're starting halfway between 0 and 1/2, which is going to be 1/4, plus, well, here's the thing. We want to start at 1/4. We don't want to move over a little delta x. So here, when we put that k minus 1, just like we have up here, when we let k equal 1, 1 minus 1 is 0. That crushes that and makes our first height for approximating rectangles there at, in fact, 1/4, and not at 0 or 1/2. So it's not a left endpoint, it's not a right endpoint. Then if you think about this, if we're going to the next midpoint, it's still going to be a delta x away from our first midpoint. So the widths of those partitions and the widths of the midpoints are going to be the same regardless. So that's what's going on there. Now the last one is pretty conceptual, and it's going to, like, it's tricky. We'll do one in class. I'm not going to get overly hung up on using the Riemann sums and taking the limits as n goes to infinity to find the true area under the curve. There's more important things for us to do, I feel, this term, than get hung up on the machinery that might bog us down. Now, the last thing we're going to do here is we're going to find a formula for the Riemann sum by dividing the interval AB into n length subintervals. You're going to use the right-hand rule for C sub k. So really, like, even though we were going to use 4 subintervals up here, I used n instead. Sorry about that. So if we were using n subintervals, this would be 2 minus, well, I guess I screwed that up a little bit, because that would be not really 1 over n. That would be 2 over n. But this right here, if we're going to divide this into n width subintervals, or n length subintervals, we're going to use the right-hand rule for C sub k. So we're using the right-hand rule, which is kind of this b right here. And I'll show you how that works. We're going to use the right-hand rule for C sub k, and we're going to take the limit as n goes to infinity to find the true area under the curve. So if we have a function f of x equals x squared plus 1 over the interval 0, 3. First thing we're going to do is calculate our delta x. Our delta x, b minus a, so 3 minus 0 over n, since we're using n rectangles, is just going to give us 3 over n. Now, really, this is a little bit bad form, because we're starting at 0. This should be a f of 0 plus 3k over n. This is our delta x. If you look back way up here to the Riemann sum, it's always our starting point, 0 in our case, plus k times a delta x. So down here, it would be a 0 plus k times our delta x. Our delta x is 3 over n. K times 3 over n is 3k over n. 0 plus 3k over n is just 3k over n. So this is representing our height in a right endpoint. If this was a left endpoint, it'd be 3 times the quantity k minus 1. But we're going to do right endpoints. They're easier. They're not easy, but they're easier. Now, this is the height of the function. This right here, 3 over n, is the width of the function. Like we did in the last class, f of 3k over n, we're applying the function value. So now to get from here to here, I'm plugging this in for x right here. When I plug 3k over n into x squared, it's going to be 3 squared, which is 9, k squared, which is k squared, n squared, which is n squared, plus 1. That is, we've just plugged this into this function right here. That's what we have. So everything else is the same. Sum of k equals 1 to n, sum of k equals 1 to n. We've applied the function notation rule right here. We're still multiplying it by this width of 3 over n. Now, to get from here to the next step, we're going to distribute this into here and here. So 3 times 3 is going to give us 27 we have here. We still have a k squared. N times n squared is n cubed. If I multiply this 3 times that 1, we have 3 over n. So we have the sum of two things. So we're going to break the sum into two pieces. So we're going to take the sum of the first piece. So we have the sum of k equals 1 to n of 27k squared over n cubed. We take the sum of this plus the sum of k equals 1 to n over 3n. Now, k is the indexing variable here. So the k's have to stay to the right of the sum. Everything else can move to the left of the sum. So this right here, the 27 can move to the left. The n cubed can move to the left. That's what's happened here. The only thing that's trapped is that k squared. Here, the 3 and the n can move through. When you do that, there's a 1 left here. So that's what we have. Now here we've gotten all the way down here, and I know this is a lot. It is for anyone, and we'll do another one of these in class, and you'll have to look at this a little bit and do one or two, but this is not the whole course. If we get down to this point, we're saying what's the sum of k equals 1 to n of k squared. This is where you have to come back here and fish out this formula here. The sum of the square integers from 1 to n is n times n plus 1 times 2n plus 1 over 6. The second one, we're summing up a constant. So it's going to be 1 times n, or c, whatever the constant is. So when we come back down here, I'm sorry for making you dizzy with the scroll. This right here is nothing more than n times n plus 1 times 2n plus 1 over 6 times our 27 over n cubed, plus 3 over n times, this is really just n times 1, which is n. Now, we're going to take the limit as n goes to infinity to find the true area under the curve. Here, I know it's been a little bit, and I'm not going to badge you down with these sorts of things. If we distribute all this crap out, the leading term would have a 27n times 2n, which would give us 54n squared, n cubed. Really, when you're talking about limits as n goes to infinity, we're really concerned about what is the leading term. And because we have an n cubed over n cubed, you can think of that as almost like a horizontal asymptote as n goes to infinity. Or you can think of in the race to infinity, they're tying. So everything that's to the right of this 54n cubed is just not growing as fast as that. It's going to kind of go away. We can cross that all off. The n cubed divided by the n cubed goes away. So that 2 times 27, that 54 over 6 is what we're getting there. 54 over 6 is 9, 9 plus 3 is 12. So really, the actual amount of area under the curve of f of x equals the parabola x squared plus 1. So a parabola shifted up 1 between 0 and 3 is 12. So there's 12 units of area underneath this curve between 0 and 3. So I know that's a lot for one session. It's recorded. Slow it down. Ask me questions tomorrow in class, and we'll do some more examples in class. Hope you guys are well.